Objective 8.6, Evaluating Logarithmic Expressions. In the second half of Chapter 8, we're going to start looking at another type of function called a logarithmic function. There are connections and relationships between logarithmic functions and exponential functions, which is why you almost always find these two functions together in the same chapter. Now today we're mostly just going to focus on expressions that have logarithms in them and how do we deal with that. So let's first start by looking at what it means to be a logarithm. A logarithm is going to fit this form. Y equals log base b of x. That's how you would read this equation. Y equals log base b of x. Now what that means is given to us here. If x is greater than 0, so this number right here that we're taking the logarithm of, if that is greater than 0, and if b, right here, the base of our log, is greater than 0 and not equal to 1, then y equals log base b of x, it will be true if and only if, that's what these IFF stands for, if and only if b to the y equals x. Okay, so let's take a look at that here. B to the y equals x. The base of our log can be rewritten as the base of an exponent. The answer from our logarithm is what would be the exponent in this exponential form. And then what this would be equal to is the x that we were taking the log of. Okay, so what this is saying is that any logarithm that is in this form can also be rewritten in this form. And if you notice here, if I take my x's and y's and swap them, okay, so if I change those two and write this as b, wow, that's really bad, isn't it? Sorry, guys. B to the x equals y. Okay, then I have an exponential form. Okay, so the x and the y just get switched and then I have an exponential form, which means logarithms and exponentials are inverse functions of each other. So just like we have square root, which is the inverse of squaring, or just like we have adding, which is the inverse of subtracting, taking the log of something is the inverse of taking something to a power. Okay? All right, so how can we use that fact? Well, first of all, we need to realize there are different types of logs. Some of them we see more often than others, and they have specific names to them. So the first type is called the common logarithm. And in the common logarithm, we have a base of 10. Now when you see it written on a paper, quiz, test, homework, whatever, it's usually written without the base. So for example, if I see this log base 10, log of x, what it means is the same as having the log base 10 of x. If there's no number written here as a subscript, then I assume it must mean that it's a base of 10. Okay? And this type of logarithm is what you're doing when you push the LOG button on your calculator. Okay, so that's what a common logarithm is. We also have something called a natural logarithm. And in a natural logarithm, the base is e. So remember that e that we talked about in objective 8.5? That's the same e we're talking about now. A logarithm with a base of e is called a natural logarithm. And usually, instead of writing log base e, we write ln. This stands for natural logarithm. It means the same thing as if we had actually written log base e of x. But we hardly ever see it written this way. It's almost always going to be written like this, ln x. And that's what's being done when you push the ln button on your calculator. Okay, so mostly today we're just going to try to kind of work with this idea of logarithms and manipulate it in ways that we can figure out answers to logarithmic expressions. So let's start with this. We're being asked to rewrite the given logarithmic statement into an equivalent exponential statement. Okay, so in each case here we have some sort of logarithm in the equation that we have to start with. And we want to use that definition of what a logarithm is to rewrite this into an exponential form. So in the first case, we're taking the log of 0.01, and that's supposed to be equal to a -2. Now, how do I rewrite this into exponential form? Well, the first thing I have to do is I have to identify what the base is. And in this case, since there isn't a base being written there, we're going to assume that it's 10. Okay, so that means that the base of my log is going to become the base of my exponent. So I'm going to have a base of 10. Now, what is the actual exponent going to be? That's going to be the answer out here. So -2 is what I need up here for the exponent. And then what's the answer to that going to be? That's going to be this part, the 0.01. Okay, and so that's exactly what we have here. 10 to the -2 power is equal to 0.01. And that should make sense, because if you think what 10 to the -2 means, it means 1 over 100, or 1/100th, which can be rewritten in decimal form as 0.01. So this really is a true statement, and so the log of 0.01 really is -2. Okay, we can do the same thing with a natural log. In this case, what is the base? Well, remember we just said that for natural logs, the base is going to be e. So we're going to take e as our log, take it to the 1.0986 power, and come back and get 3 as an answer. Okay, so my base of e, right there, gets taken to the 1.0986 power, and that's going to end up giving me 3 as an answer. This exponential form means the same thing as this logarithmic form. And then in our third example, we have a different kind of log where the base is 4. Even though that's not a particularly common log to use, How we are going to work with it is the same as what we're going to do with common logs and with natural logs. We're going to start with the base, which is 4. We're going to take it to the third power, and we're going to say that that's equal to the 64. Okay, which is true. 4 times 4 is 16. 16 times 4 is 64. So 4 cubed equals 64, which means the same as taking the fourth log, or log base 4, of 64 and making it equal to 3. Okay? Now we can also go the other way. We can be given the exponential statement, and then we are expected to come up with the logarithmic statement. So if we start with the exponential statement of 10 to the negative third power equals 0.001, now we have to ask ourselves, what is the base of the log going to be? Well, remember, the base of the log is the same as the base of the exponent. So we know that the base of our log is going to have to be 10, which will make this a common log. Now, what are we going to take the log of? Well, we're going to take the log of this 0.001. Remember, we're doing inverses, so we take the log of what it's equal to end up with something over here. So if I take the log of the 0.001, then that's going to end up being equal to this -3 that I have as an exponent. So I can rewrite this exponential form into this logarithmic form. Remember, if I don't write anything for the subscript, that automatically means a base of 10. So the log of 0.001, right here, has to equal the -3 that was right here. Okay, how about the next one? If I have 10 to the power of 7k equals r, what would be the logarithmic statement for that one? Well, again, we're starting with a base of 10, so we're going to use a common log, which would also have a base of 10. We're going to take the log of the r so that we get an answer of the 7k. So the log of r has to equal the 7k. Okay? Now what about this case? We've got 5 cubed equal to 125. This time the base of our exponent is 5. So the base of my logarithm will be 5. So now I'm going to take the log base 5 of the 125 to get the 3 for the answer. And finally, if I have e to the 4u power equal to m, now because the base of the exponent is e, I need the base of my logarithm to be e, and that is a natural log. So I will say that natural log, ln, log base e, remember, same thing, ln of the m is going to have to equal the exponent of 4u. Okay? All right, so why don't you stop the video for a moment and go ahead and try these. Whichever form it's currently in, you want to rewrite it into the other form. So if the current statement is in exponential form, then you want to write it into a logarithmic form. If the current statement is logarithmic, then you want to write it in exponential. Pause for a moment while you work these out and come back when you're ready to check. All right, so here are the answers that you should come up with. In the first case, we have a base of 10, so we're going to take a common log of the 10,000 to end up with an answer of 4, right there. In the second case, we start with the log, so we have to look at the base of the log to know what the base of the exponent should be, and that's going to be 10. And then we'll take that to the negative 1 power to end up with an answer of 0.1. In this case, since we have the ln, that means we have a base of e, so that's the base that we need in the exponent. And then we're going to take that e to the 5th power here in order to end up with the 148.413 as our answer. And finally, when we have the exponential form 3 to the 2x equals 81, we're going to use the 3 as the base on our log, take log base 3 of the 81, and we end up with this exponent 2x as our answer. So those are the answers you should have to these example problems. Now we can build on the same idea as a way of actually evaluating a logarithmic expression. So if we're asked to evaluate without a calculator and we're given something like the log base 6 of 216, what we can do is say, well, I know that has to be equal to some answer. So let's call that answer y. Okay, well, when I do that, I have now set this up as a logarithmic equation, just like I was doing in the previous examples. And so I can take this logarithmic equation and I can rewrite it as an exponential equation. So as an exponential equation, I would have 6 to the y power equal to 216. Okay, and then you can just ask yourself, so what number would I need for y so that when I take 6 to that power, I would get 216? Well, we know 6 squared is a 36. So if I take 36 times another 6, that's what's going to give me 216. And so therefore the y is going to equal 3. So the log base 6 of 216 has to equal 3, because that's what it would take for the exponent to take 6 to some power and get 216 as an answer. Okay, same thing in this case. If I want the natural log of the 5th root of e, if I start by thinking of this as being equal to some number y, okay, then I can rewrite this using a base of e, because remember natural log is a base e. So e to the y power would have to equal the 5th root of e. Okay, now this may not look particularly easy to figure out at the moment, but if we go back to what we learned in chapter 7 last year about radicals and rational exponents, we should be able to recognize that the 5th root of e is the same as e to the 1/5 power. Okay, I'm sorry about my writing utensil here. Since they redid the operating system, my bamboo's not working so well, so I'll have to find another mechanism for doing the writing. Okay, so that's supposed to be an e. Sorry about that. So 5th root of e is the same as e to the 1/5 power. So now if I have e to the y, and it has to be equal to e to the 1/5, then what does y have to equal? Obviously, it has to equal 1/5. Okay, let's Let's do the same thing with the next one. See if we can get the pen to work on this. So I have the log of 10 to the square root of 43 power. So I'm taking the log of this whole thing. And again, with no number written there, that automatically means it's 10. So if I set this equal to y, okay, then I can rewrite it as 10 to the y power being equal to this whole thing, 10 to the square root of 43. Okay, so again, if 10 to the y has to equal 10 to the square root of 43 power, then what does y have to equal? Well, it's just going to equal that square root of 43. Okay, and then finally, going the other way, we're actually starting with an exponential expression here. But the same thing, if I set that equal to a y, okay, then I know the e base here means I'm going to need an ln as my logarithm. What I'm going to take the ln of is this y, and that has to be equal to this whole exponent of ln x squared. Okay, well, if ln of y has to equal ln of x squared, doesn't it make sense that the y and the x squared must have to be equal to each other? So e to the power of ln x squared is just going to end up being equal to x squared. Okay, so go ahead and take a moment and try a couple of those. We've got log base 3 of 243 and then the natural log of 1 over e. See if you can figure out what those should be equal to, and then come back when you're ready to check your answer. Alright, so here's what your answer should look like. In the first case, we have the log base 3 of 243. So we can rewrite that in exponential form as 3 to the x or 3 to the y, whatever variable you want to use, equals 243. And then the number that we actually need for an exponent would be a 5. So x would have to equal 5. In this case, since we're using natural log, we need to recognize that my base is going to be an e. Raise e to the x, and I need to get 1 over e. But again, as the fraction 1 over e, that may not be very easy to figure out. So I need to rewrite the fraction in an exponent form, which would be e to the negative 1. Then it becomes very easy to see that x would have to equal negative 1, and so that's going to be my answer. All right, finally, a couple of properties that are helpful with logarithms to be able to identify, because when you can identify these things, it gives you some shortcuts on how to figure out your answers. Okay, so the first thing you need to know, it kind of goes along with the definition of what a logarithm is and when you can use it. And that is that if you're going to take the log of some number or some expression, this is only going to work if that v, whether it's a number or an expression, whatever it is greater than 0. You cannot take a logarithm of 0, and you cannot take a logarithm of a negative number. And it doesn't matter if it's a common log with base 10, whether it's a natural log with base e, or whether it's some other log with some other base b. You have to make sure that whatever you're taking the log of is going to be greater than 0. So that's the first property that has to hold true for all logarithms. Okay, now for a couple of shortcuts. What happens when you take the log of 1, whether it's a common log, a natural log, or a log base b? Well, let's just look at the common log here for a second. If I go back to what we did in the last example, I'd be looking at a base here of 10. So I'm basically saying 10 to what exponent is going to give me 1. Okay? Well, we know that regardless of what the base is, if I'm going to end up with an answer of 1, then that means the exponent has to be 0. Okay? Similarly here, if I use the 10 and rewrite it as 10 to some exponent has to equal 10, then I think it's pretty obvious that x has got to be 1. Okay? So taking the log of 1 always gives you 0, and taking a common log of 10 will always give you 1, because the base of the log and what you're taking the log of match. Okay? So that's what happens with these other types of logs as well. Any time you take the log of 1, whether it's common log, natural log, or a base of some other kind, you're always in this situation where you're taking some base to some power to get 1 as an answer. So those are always going to give you an answer of 1, or excuse me, of 0. Okay? Whereas on the other side, the other part of this is anytime your base on your log matches the number you're taking the log of, you're always going to be in this kind of situation where your exponent has to be 1. So here we've got a base of e, and then we have the e that we're taking natural log of, so that's going to be 1. Or here we've got a base of b, and then we're trying to take the log of b, so that's going to be 1. Now you can always work these out like we were doing in the previous examples, but if you can actually recognize these kinds of special situations, then you should be able to just quickly snap off what the answers are. Okay, a couple more quick ones and then we'll get finished up. If I am taking the log of something to an exponent, again, if I were to actually work this out and rewrite it in exponent form, what I would find is if the base of my log matches the base of this exponent, then in a sense the log and the base cancel out. And so all you're left with is just the exponent. So same thing here. Natural log ln means a base of e. So this e matches this e, which means the natural log of e to the k. Those will cancel out, and all you'll have left is k. And then similarly here, no matter what your base is on your log, if it matches the base on your exponent, they're going to cancel each other out, and you're just left with the k. And then kind of vice versa of that, if we have an exponential form where we have a log in the exponent that has a base that matches the base of the exponent. I know that's a lot to take in, but let me say that one more time. We are looking at an exponent here, right? This whole thing is an exponent. And in the exponent spot, there's a log. If the base of that log matches the base of your exponent, then again, if you were to actually work this out, you'll find that basically these just cancel each other out and you're left with the v. As long as that v is something greater than 0, that's what you'll be left with. And it's the same with the other two types as well. This e matches the base on ln, so they're going to cancel out, and we're left with just v. This b matches the b base on that. They cancel each other out. We're left with just v. Okay, so try to recognize those situations as much as possible because it can make figuring out your answers a whole lot easier. So let's just try a few here quick. Take a second to try these on your own, then come back and check them and we'll finish things up. Alright, so in the first example, we've got 10 as the base here on our log. We've got 10 as the base here. That means our answer is just going to end up being the 3. Here we've got a log of base 2. We're taking the log of 2. Since those two match up, we're just going to have a 1 for our answer. In this case, we're taking the natural log of 1. Taking any kind of logarithm of 1 always gives us 0 as an answer. And in our fourth example, the 10 in this base matches the 10 in this base, so they cancel out and we're left with the 0.5 as an answer. Okay, I know that seems like a lot of kind of detail, nitty-gritty stuff, but it really is just the kinds of problems that you only get better at if you just do them and practice them and go back to your notes and go back and forth and just figure out what that pattern is for rewriting back and forth between exponential and logarithmic forms. So use this video and your notes to help you complete the 8.6 practice. Make sure you ask questions in class if any of this is still just a little bit confusing. And when you finish with the objective, make sure you show it to Mrs. Gordon so she can check it off. We'll see you next class.